Okay. Can you put Giovanni, can you put the computer somewhere? Just are you complete?
I don't know. We can say, have anyone seen anyone else?
Where are the youngsters? So to
Yeah,
say?
well,
Yes.
Well, it's one exception. But Alak should be in. Anyway, so
Okay. I'll start and they could join that.
yeah, okay. So
yeah. Just let me.
No. I don't know, sometimes Philip writes in Telegram, right?
Yeah.
Someone,
Yeah.
no one else wrote the same. I don't know.
Are you already recording it?
yes, I'm recording that one. And Giovanni Solda is in the Wachtraum.
Yeah.
Yeah, so got to yeah. You have to check.
Maybe. Now it should be better.
Yes, yes.
Yeah,
But you
yeah,
have to
sure.
check when others might join
but
in. So
yeah.
could be that
Could
David
be.
Bélanger wants to move in.
Wait, how do you say pin?
What?
It would be good to pin yours since well.
What?
And since I don't, well, no, you should register correctly. But you never know.
But I cannot see me now. Well, anyway,
Yeah, that's why.
can you see me on your
Yes.
screen? Okay. So what I'm speaking about is rewriting. And logic. Now, don't need to know what a term writing system is, but I also assume that you know what a term is. Say, term over a set of function symbols that is used now. So let F the signature. Means a set of function symbols with LTs. And now the rewrite system just find a set up over a set of term T or function symbols and a set of variables X. Just is our context finite. In general, it can only be infinite. Just occasionally finite set of order pairs. Where the variables in the right-hand side are contained in the variables of the left-hand side. This is just a technical condition. Basically, if this is not satisfied, then you always get non-terminating systems, which we don't have. Now, if you have a set of rewrite rules, this is a set of rules for simplifying terms. So what is the idea? The idea is we have two terms S and T. I want to check whether our given set of equations S is provably equal to T. And the idea is we simplify S as much as we can with the rewrite system. We simplify T as much as we can with the rewrite system. And if the corresponding normal forms are equal, then S and T are probably equal. Yeah.
I couldn't get what are the rules for
the rules is just a set of ordered pairs.
Okay, and each pair is
Finite set
L, I,
of
and
pairs.
I are terms, just terms?
Pairs of terms.
Okay.
And okay, now the question is how to simplify terms, and this is coming from the rewrite relation. This uses rewrite relation. The question is how can we use rules to simplify terms? And the reduction relation is not this way. And there are two rules. If sigma mapping and the variables of x and the set of terms, sigma is set including. And if what are there is the Riemann rule, then we can take the left-hand side, apply substitution sigma, and can rewrite it to the right-hand side, we apply substitution sigma. So we are allowed to plug in some values for the variables. And second, rewrite relation is stable under context. So if we are going into term and then look into subterm, we can do the rewrite step at the subterm. So it means if S equals to T, then in the situation F of, and there's an immediate subterm S. And then we can write to of T. So the rewrite system is a finite set of pairs, and the rewrite system induces a rewrite relation. Now you want to see an example. Simple example. The signature F is given by symbols for the Ackermann function. So what do we need? A simple binary for the Ackermann function, and we need the symbol for the successor function and for 0. And then we have certain rules. A 0 and x rewrites to successor of x. A, maybe I write y here. A of x plus 1 and 0 rewrites to A of 6 and 1. 1 is successor of 0. And A of x plus 1. A plus 1 rewrites to A of x and then A of successor of x and 1. So the defining equations of the Ackermann function are turned into rewrite rules. And then if you have a closed term over the signature, one can use these rewrite rules to reduce every closed term to a corresponding numeral, and the numeral will be the value of the term. Oh, I go not too much into the details. So this is an example of a system which will terminate, so there will be no infinite sequence of reductions. We say a rewrite system R is terminating. If there is no infinite sequence, as I, such that I sub I rewrites to sub I plus 1. Okay, and now the question I will investigate in this talk is, assume you have proved termination for a rewrite system. What can you say about the length of longest possible reductions? Now we have to know what are methods for proving termination. And the classical way to prove termination is using certain reduction orderings. And that's the so-called lexicographic path ordering. And it is defined as follows. So the question is, where does the lexicographic come from? So let F be a signature consisting of finitely many Banach symbols. And T are open terms, complete variables. And we say S is bigger than 3. And this is defined by recursion. So First of all, if t is a variable showing up in S, and S is not the variable, then t is smaller than S. First one is t is a variable of S, and S, fine. Then we have second. There are certain clauses. Term S is a composed one. Has a form Fk. Is 1 to Sn. Term T has a form Fl. 1 to Tn. And there are 3 conditions. And either it happens that term T is recursively less than or equal to one of those subterms. Now this relation here means it's bigger with respect to this O-ring or is equal to. Second condition is here we have numbers 1 to k. K and L are from the set. So we compare K and L. K is bigger than L. And all subterms here are smaller than S. So for all k less than to N, we have S is bigger than K. And the third one is K is equal to L. So this symbol here is the same symbol as this one. And then we order the sequence of subterms lexicographically. So there is an I0, it's equal to M, such that you order from the left to the right. So S1 T1, Si0 minus 1 equal to Ti0 minus 1. At position I0, we have Si0 is lexicographic bigger than I0. And for the remaining subterms, we assume that they are smaller than S. And for all j less than N, we have that Tj, that S is bigger than J. Okay, this one is called lexicographic path ordering. And one can show that this is a so-called well-founded ordering. So there's no strictly descending chain of terms with respect to lexicographic ordering. And then for proving termination of a rewrite system, one way is to say that I can order the rewrite system according to this ordering. Now, to make it work, we need 2 properties. Namely, if S is bigger than T, and if we apply a substitution, then sigma S is bigger than sigma of T. And secondly, if S is bigger than T, then this transfers to subterms. So it reflects basically these 2 properties. And so by knowing that lexicographic path ordering is well-founded, and if we know that we can order all the roots using this ordering, then we can guarantee termination. Now, I will not give a proof of termination. Actually, we will not need it for our purpose. But now we come back to our example. It's a nice reader system. And this is terminating under this ordering. Why is this the case? Well, the O-ring is, this one is bigger than this one, let's say bigger than this one, in the O-ring of the function symbols. Y is smaller than this term here, because y is a variable of this term. S is smaller than this function symbol, then S of y is smaller than this term. Now here we use +1 is double. Here we use lexicographic comparison. These function symbols are the same. X is smaller than S of x. And S of 0 is smaller than the whole term because 0 is contained. And S is considered to be smaller than this one. And why is this ordered lexicographically? Well, we see here is S of x, this is x. So this ordered pair here is lexicographically smaller than this ordered pair here. Now we have to check the last condition, namely that all subterms here have to be smaller than the whole term. And then we look at this term here. This term here is again smaller than the whole term here because it's S of x. But in the lexicographic comparison, we now go to the second coordinate, and y is smaller than S of y. So that's fine. So this example, this terminates under the lexicographic class. Now, what's the surprising thing is, what I wanted to show is, so what we see here is lexicographic path ordering is very powerful. You can prove termination for rewrite systems which are reducing enormous complexity, namely the Ackermann function. And I will prove a reversal, namely you cannot do more. So basically, what is the idea? If R is terminating, under the lexicographic class ordering, then the derivation lengths are bounded by Ackermann function. In finitely many variables. Finitely many arguments. So you can imagine, you can generalize this definition to n arguments, and then you get a common function growing faster than the usual one. And that's basically what I want to show today. And this is one of my first results, which I proved in my career. So now the question is, what are the Ackermann functions and variables? What is a nice way to represent them? And for this, it's convenient to study small ordinals. And they are just lexicographic orderings or tuples, so no need of ordinals really used. So if I have a k plus 1 tuple, I order them in this way. And those tuples, if they have the same length, they are ordered lexicographically. These are these ordinals. And the maximal coefficient of alpha is the biggest natural number showing up in these coefficients. Maximum taken over NK from 0. What else do I need? I need the notion of fundamental sequence. So if I have a limit element, meaning the last term here is 0, then I have some infinite ordinal of limit type. And for this, I can use the fundamental sequence. So if M0 is bigger than 0, then I have here basically a successor. So omega to the 0 times m0 is basically m0. And if m0 is bigger than 0, then I have a successor only. Then what you would expect, right? Is omega to the k, omega to the 0 times m0 minus 1. And otherwise, then the form omega k mk plus omega to the L ml with some L bigger than 0 and ml bigger than 0. But assuming that alpha is not 0, right? And then alpha x will be a strict one over here. I go one level below and I'm not down here by this one. And then one can show if we are in this case, these numbers basically converge. Why I'm doing so? Because I want to define the Ackermann functions in n variables in a compact way. Well, we define functions with alpha, so natural numbers to natural numbers. I start with some function, could be x plus 1, could be x, but it's not so important. Now, if I'm in this case, I have alpha plus 1. This is an f of alpha. I iterated x plus 1 many times. X. And if I'm in this case, so-called limit case, then I take the what is basically the idea? Basically, the idea is if I have an Ackermann function in, let's say, k plus 1 many variables, corresponds basically to f index omega to the k times nk plus 1 plus omega to the 0 times m1 plus m0. This is this type of transition, but to do calculations, it's easier to work with f functions, but an in-area Ackermann function is basically with this shape. We need certain properties. What you would expect over those functions is they are just getting speed and speed and speed. They behave like the Ackermann function. So first of all, what will be monotone functions? Voilà. No surprise. The Ackermann function itself is also monotone. Now, second, and alpha of x as a property, it's strictly bigger than the maximal coefficient of alpha. Just imagine the dth branch of the Ackermann function is bigger than d. It's not a big surprise. The maximal coefficient is this one. So we go into this index, check what is the biggest natural number showing up here, and this function is bigger than this number. Not a big surprise. And number 3 is if alpha is less than beta, we want that f alpha is eventually dominated by f beta. Now the question is, when does the domination start? The point is, if the maximum coefficient of alpha is bounded by x, then basically if alpha of x is smaller than this one, and if I enlarge x by y, then I have this property. That's important. The basic lemma to compare these functions. And once you have these properties, you are fine. You don't need more about the Weiermann function. These Weiermann functions. Okay. And now the question is, how can we relate these functions to this ordering? No, first I will clean it of the code.
Exactly fast ordering, because I have some questions about it, but I think
Yes.
some of them related to what we're talking about now, so I just ask them.
Yeah,
It's not a big deal.
yeah. But for the experts, of course, it's clearly related to the what's called theorem by Kruskel.
Yes, very exactly what I could talk.
Yes,
So because, yeah, I do my graph now. So basically, the definition, I think if you slightly modify the definition,
Yes.
maybe so you have this last item, so where, so the theoretical, so I think, in item 2.3, you demand that S0 is bigger than, yeah, I think it modifies this clause to, by replacing S0 to S. Then this basically would be this ordering that you need kind of corresponding to this 2.3 Boolean functions.
Yeah.
And basically, I guess what we need to say to obtain this optimal bounds for this restricted force of Kruskel. So when can fix labels for fixed branching.
Yeah.
Anyway,
So what is our strategy? Strategy is very simple. Well, how to prove bounds on lengths of derivations? Well, the idea is define the function I. And now I assume that I have also some closed terms, which means I have some constants available. Otherwise, I consider the but anyway, I need the relation I from the constants into the natural numbers, such that then what if S rewrites the T, then the number is limited to S is bigger than the number is limited to. Well, why is this interesting? Well, if let's say we have a real sequence of terms, then what we would get is a descending sequence of natural numbers. And clearly, the sequence cannot be infinite, because there's no strictly descending sequence of natural numbers. But moreover, follows that n is bounded by the extension of the first term. So we get two results in one step, namely we get termination and we get bounds on the lengths of longest possible derivations just by looking at the value of the first term. So that is what we are now going to do. We will define such a function I, such that if a Riemann system is terminating under Lexwell's parser ring, then this is true. Okay, so what is the goal? The next theorem to assume F is a finite signature. Okay, and assume R is the finite integral system. Let A be the maximum taken over the arities function to the F in the signature. So let's say maximum over the arities of L, where L is less than K. So that's finite information given in advance. And let D equal to the maximum. Every term can be considered as a tree, and a tree has a certain depth. And I take the maximum depth the right hand side of the rewrite system. Since the rewrite system is finite, that's a finite number. And now comes the trick. To assume that S is the first term, Sk is 1 to Sn. Now that straight forwardly define I of S. I use my function, the common function. Here take here take +1. Make it slightly bigger than for the entities. F omega to the A times K plus omega to the M times interpretation of S1 plus omega to the 1 times interpretation of S1 plus 1 of G. So what I do is I have an outermost index. This A is bigger than all the entities. I multiply it with the index of the function, and then I fill somewhat lexicographically up the remaining values of the subterms. Now it could happen that Fk is a constant. If Fk is a constant, these terms just disappear. The number D is the number coming from the rewrite system. And it's important that here is a +1. And the role of the +1 will come in the proof. But you don't see it yet. And then assume further that L bigger than LPO here for all roots in the rewrite system. So assume that the rewrite system is terminating under lexicographic sparkling. And then the claim is if S rewrites to T for the rewrite system, then I have T. So that's interesting. So, and this is somehow the difficulty in the problem is before we start, we define our interpretation function. And for this, I use the n-area Ackermann function. And then I claim if S rewrites to T, then the left-hand side is bigger than the right-hand side. But you can understand how to set up a proof is try and error. You define your function I, and then you do a calculation. When you succeed, you are done. When you don't succeed, you have to do a new try. And so basically, I could stop here and say that's all. Then you want to understand what I'm doing here, right? But the proof is somehow interesting. And it just is growing from the bottom. You just do all the steps, and then finally the result comes out. But it's a nice finding. So somehow with lexicographic path ordering you can show termination of these Henry Ackermann functions. And this theorem says when you cannot do more, then whatever you do, with lexicographic path ordering, the Henry Ackermann functions will dominate whatever you obtain. Moreover, the proof is so strong that you even don't need that the lexicographic path ordering is well founded. I just prove this one without assuming that the lexicographic path ordering is well founded. I define this function here, and this proves if I have a real system contains the lexicographic path ordering, then it's terminating. So I even don't need the abstract argument. Okay. How to do so? Well, first of all, what? Just kidding. Yeah, I just thought I've forgotten some part in the manuscript. I found it. So this will be the first lemma. So assume fk is the constant function symbol, and assume that fk is lexicographic bigger than t. Then t has to be a closed term. Of course, one can show if a lexicographic comparison, then the variables of the right-hand side are always contained in the left-hand side. Then we have what? Well, we want to show that the interpretation of fk is bigger than the interpretation of t. But we cannot do so. So what we have to do is we have to show the intermediate step. Then we have to show this one. So this is not the same as this one, but it's almost the same. But this is the statement depending on the dynamics of t. The dynamics of t is measured by the upper index depth of t. And important, here is in this +1 missing. Here is the +1 showing up. And then you see the +1 is needed for moving things into the exponent. Okay, the proof here is easy going. This is my hope. Yeah. So the first case is t would also be constant, right? Then t is a constant. T is a form fa. Now we have to look. So I will not delete the definition of the ordering. So when is such term bigger than another constant? There's only the case that k is bigger than n. Then k is bigger than n. and f omega a times k, depth of t is 0, to the 1 of d, has to be bigger than interpretation of t. Well, interpretation of t is this term with a plus 1. So this is f omega to the a, but now the point is L plus 1 of d. Now you see this L is smaller than this K, so this number here is smaller than this number, and the coefficients here are bounded by this term. So in this case we are done. Okay, second case. The depth of T is bigger than 0. Here's a form as L divided to N. And bigger than 0. What does this mean? It cannot be the case that we are in this case, because then if L is really constant. Right? Okay, what can happen? Can it happen that T is less than or equal to a subterm of Fk? No, Fk is no subterm. So the only thing is here in this case, E is also not a variable, right? So then Fk bigger than T means K is bigger than L, and all subterms of T. Fk is bigger than all T J. J is equal to N. Okay, and now comes the induction hypothesis. This is a subterm with smaller depths. So we do the proof here by induction of T. The induction hypothesis gives what? F omega to the a times k, depths of dj plus 1. That is all bounded by the depths of T. So that's followed by the induction hypothesis. Now then, let us look at interpretation of term T. It's Fl subterms, so I get F omega to the a times L plus, then comes a list of subterms, omega to the n times interpretation of T1 plus omega 1 interpretation of Tn plus 1 and d. Now you have to compare it, you have to show that this is smaller than F omega to the a times k to the depth of T plus 1. So why is this the case? The point is this number here, the whole number, starts with omega to the a times L, but L is smaller than k. So this term here is roughly smaller than this term here. So we have one is smaller than the other. Now I have to check what is with the maximal coefficient. The maximal coefficient here is given by the maximum over L, the subterms. The subterms are under control by this term. Yeah, and L is bounded by K, that's also fine. So we are done. So the lexicographic comparison is precisely what's coming out of but you see how now it works. Just we we are working on this one. And instead of directly proving that one, we show this one for approximations. We'll need some space. Maybe I get rid of this one. This is needed in a minute, so I will not wipe it out. Yeah, the next one. Assume what? S is bigger than 20. Now I'm working with open tone. And assume that the depth of T bounded by number D. Then we have for all substitutions from variables of those terms. So the interpretation of sigma of S is bigger than the potential of. So what is here the trick? The trick is basically I want to show this property here for closed terms, but closed terms can appear as values of closed substitutions of open terms. Therefore, I'm here to deal with open terms. And finally, we get the implications for closed terms. Proof. And now this is somewhat difficult. It's now the heart of the matter. So we do it by induction on the complexity and depth of S. And in the proof, we do a subsidiary induction on the depth of T. So that makes life difficult, but anyway, we start with depth of S equal to 0. First, is depth of S equal to 0. What does it mean? It means then S equal constant sum of K. And by the previous lemma, by lemma 1, we get interpretation of sigma of S. Now S is a constant. There's nothing to substitute. This is F omega A times A plus 1 of T by using this definition where these terms are empty. What's plus 1 is what it means. This is plus 1 mean. Of course, yeah, now comes here the trick. The depth of T is bounded by D. Right, so this is at least S F omega A times K becomes D plus 1 of D. But D is bounding the depth of T. So I can plug in this value. Which is bigger than interpretation of T. And T has to be closed because S is closed. This is a rotation of sigma of T. So now we see the role of lemma 1. It fits precisely in the proof for lemma 2. Yeah.
Okay, I realize. Okay,
I should not write all that definition.
I don't know, I mean.
Yeah, it might be reasonable. Right. So I will wipe out this. Lemma 1 is discarded because I used it already and I don't need it any longer. But the argument used for lemma 1 is basically now used also in the proof right now. So what? In our case, depth of S is bigger than 0. S is a form that K is 1 to S. Now, what does the induction hypothesis say? It says for all these subterms, I can apply induction. So induction hypothesis says if I have some S I, here and equal some term U, and the depth of U is bounded by me, and then I sigma of Si is bigger than I sigma of U. Now comes a new claim. What I'm going to show is this one here. But as you remember from proof of lemma 1, before showing such a thing, I have to do a dynamic proof depending on the complexity of T. So the claim is if S is bigger than T and the depth is bounded by T, then what? I basically take the approximation of the interpretation of this term. So it's omega to the A times K plus omega to the N interpretation of sigma S1 plus omega 1 times interpretation of sigma of Sn of D. So interpretation of S would be this term plus 1. Now I delete the plus 1. And I smuggle in the depths of T. That's one exponent. And this will be bigger than the interpretation of sigma of T. So in the proof, I use main induction on the depths of S. It's a main induction hypothesis. And then make a new claim in the proof dealing with the right-hand sides. So I'm dealing here with those ones. And now I have to use subsidiary induction on the depths of T. And okay, proof. Now you have to look back at the definition, which luckily is not fully wiped out. So we have the first case. First case is simple. Case 1 is T is a variable of S. S is this term, then basically T is a variable of one of these subterms. And now one of the lemmas I wiped out is that alpha of x is bigger than the maximal coefficient of alpha. Now, when you look here into this interpretation of a term, the subterms showing up here as elements of the maximal coefficient. Now, a whole term is bigger than all immediate subterms. And if T is a variable of S, then sigma of T is some direct subterm of sigma of T is a direct subterm somewhere deeply inside term S. So sigma of T is a subterm of sigma of S. So then, by iteratively using this property, so I call this order here maybe alpha. Then F alpha of D is bigger than the maximal coefficient of alpha, and either sigma of T is equal to one of those ones, or I use this lemma again. So I get here I sigma of T. So this property here is basically guaranteeing that interpretations terms are always bigger than the interpretations of subterms. And this is used already. Now, what's left? What's left is this case. But this is basically the same, right? So 2.1. SI is a big as T. Yeah, it's simple, right? The main induction hypothesis gives that interpretation of sigma of T is less than equal to the interpretation of sigma SI. And that's bounded by F alpha of D, because sigma of SI, here's interpretation of S, interpretation of sigma of S, and here are the interpretations of the sigma of SI. So that's all clear. Okay, and then there are two cases left, this one and this one. 2.2 is not too difficult. But don't worry, the argument is finished in half a page. So. So we are considering now 2.2. What does 2.2 say? A is bigger than L, and S is bigger than all subterms Tj for all J is equal to N. For this situation, I can apply the subsidiary induction hypothesis, because the Tj are subterms of T, they fulfill this property, And so the induction hypothesis is what? F alpha, then the depth of Ej plus 1, upper bound is the depth of E. Of B bigger than I sigma to J. Or now what? Now we have to consider alpha of alpha depth of E of D. So this plus 1 gives another iteration of the function f alpha. And I have to show that the right hand side is smaller than that one. So I have to show what? This is bigger than. Now I put here the interpretation of the right hand side. So it's omega A times L plus omega times the n times interpretation of sigma S1 plus omega n times interpretation of sigma of Sn. Now the question is, why is this the case? We have to look at alpha. Alpha is this term. Now you see why I'm moving this term here to the left. It's the most important part, so to say. And K is bigger than L. So alpha is bigger than this number beta. Because omega A is only this times L. And here in alpha, I have omega to the A times K. Now I want to apply this lemma here. So ordinal alpha is smaller than the other ordinal, and the maximum coefficient of alpha. So this number is smaller than this number. What can we say about the maximum coefficient here? These are the biggest natural numbers showing up here. These are L and these interpretations of these subterms. I'm wrong over here. T, yeah. T is the form of L 1 to N. So here I need one here. Anyway, so the argument why alpha is bigger than this ordinal remains the same. But now I need to estimate the numbers showing up in this term by this argument over here. But this is basically what we obtain by the substitute induction hypothesis. Therefore, we are done in this case. So this is So you see the argument just flows by itself. Whatever you need just comes out of the situation. And now the final step is this one here. And that's now by magic. So that's the most difficult part. So where do I do it? So what's the point? The point is I have the following situation. I have S is Fk. Here's some Si0. And it's bigger than term T, which starts with the same function symbol Fk. And at position I0, I have T I0. and this one is bigger than this one. Lexicographic comparison, right? It's this comparison. You can say, so here is S1, here is S1, and the first one where this is changed is position I0. This is the situation. Okay. Yeah. Now, let us just jump into this case. The interpretation of sigma of t is f omega to the a. Now the point is here comes the k. This in both cases the same. K is equal to L, but this also means that the length of this tuple is the same length of this tuple. Then comes here omega to the n, interpretation of sigma S1 plus. Now we come at the situation where this term shows up. It's omega to the m. Yeah, now we have to subtract 0 plus 1 maybe. And then at the end, I have omega to the 1, interpretation of sigma S M. So this is T. This is T, then it's not SI0, but here it is T alpha. Okay, now just have a look. So I make so this is the definition of I sigma T. So just have a look here. K is equal to L. This one is S1. Here's one position. We have the statement of negative M minus I0 plus 1 of I of sigma of here is T1, sigma T I0. Here's omega 1 interpretation of sigma. That's this one. Now, just consider this alpha from before. The alpha from before is omega to the L times K plus omega to the N. I sigma S1 plus comes to position where Ti0 and Si0 makes a difference. So here's I sigma Si0. But without the plus 1. Here's the plus 1. Okay. Interpretation. But here is without the plus 1. So this is basically alpha. Now I have F alpha depths of T of D. So I take here the depths of T. And an odd iteration of F alpha. And the claim is this one is smaller than this one. Well, why should this be the case? The point is we have to look at alpha. So I'm claiming this number here, the number beta. Beta is smaller than alpha. Why it is the case? Well, look, here are the same. Well, sigma T1 and sigma S1 are the same because we have here the lexicographic comparison. So this one is the same, this one is the same, it's fine. Suddenly here's a difference. The difference is now fine. And now comes a moment, the final end of the proof, that I use the main induction hypothesis, namely Si0 is bigger than Ti0, and the depth of Ti0 is bounded by V, therefore I have this one. So jumping at this position, this number is bigger than this number. So this number is bigger. And what comes next doesn't play a role for the lexicographic comparison. So I just go into the term and compare from the left to the right. These indices are all the same up to this moment. The main induction hypothesis says this one is bigger than this one, and then this beta is smaller than alpha. Now, beta smaller than alpha does not suffice. I have to know what is the maximal coefficient. So I have to check what do I know here about the numbers. Do I have some under control? And the answer is the subsidiary induction hypothesis says all these numbers showing up here are bounded by this inner argument. Therefore, I can apply this lemma, and therefore I'm done. And you see how nicely the argument fits together. So you do a double induction. The main induction hypothesis gives this important moment, the lexicographic comparison. And the subsidiary induction hypothesis gives the information on that the number theoretic content is under control. Well, that's good. But we are not yet done. But we are basically done. Namely, so I know why not. Yeah, the lemma is important. Yeah, we come back to the main theorem. So we assume that I have that in my Hilbert system, for all roots, L is bigger than R. I had these components, number D was maximal depth the right hand side for Hilbert rule. A was a number bigger, was the maximum arity functions in the F with the signatures. Okay, and now what I want to show is if S resides to B, then interpretation of S is bigger than now we are not yet done, but we just collect what we have. So proof. Well, what can be the reason that S resides to T? First one is there exists a rewrite rule. Rewrite rule. And a substitution. Substitution such that sigma L then rewrites to sigma alpha. Now, since we have a finite reverse system, we have this finite number d. Then by the lemma, it follows that I sigma L is bigger than I sigma R. Well, did I really show it? Maybe not yet. What I showed is I was one step early. So I showed basically what that I sigma. I showed that if alpha depth of t, one of t is bigger than I sigma s. But if the depth of t is bounded by number t, and it's bounded by f alpha plus 1 of d, that is interpretation of the left-hand side. So I just gave the iteration argument, but then you need finally to plug in the definition of the left-hand side with a plus 1 to move the iteration index depth t plus 1 into this plus 1. Okay, that's fine. So by the lemma, we have this one. That's fine. That's the first part. And the second part is it could be that term s in the form f of s prime. Rewrite into term t, the form f of prime in a context. Let's say it's an fk because of s prime divided by t. And then it's easy. Then the interpretation of S is, now comes the term, blah, blah, blah. In the term, I have the interpretation of S prime. Interpretation of S prime is bigger than the interpretation of T prime. So the induction hypothesis is interpretation of S prime is bigger than interpretation of T prime. Now if I have here S term, some D here and D here. There will be more tonicity because if this number is bigger than this number, then the corresponding ordinal here is bounding the corresponding ordinal here. And the natural numbers showing up here are then basically the natural numbers showing up here, except in this case, but this number is bounded by this number. So the content here is bounded by the content here. And we have the lemma that the content is bounded by the whole term. So this ordinal is smaller than this ordinal. The content is bounded by the whole term. No, this is not the right argument. But anyway, it does not matter too much. Not matter much. No. Do I need here? Well, I need more tonicity here that this number is bounded by this number. But this is not a big problem because all the information here is bounded by the information over here. So, yeah. I did not prove it yet, but this is a lemma which will be true. So this holds by third lemma on the alpha, which I did not write on the board, but it will work out. It's basically the lemma that every Ackermann function is monotone in each argument, which is a big surprise. Okay, that's basically what I wanted to show about the lexicographic path ordering. That is a sort of interesting calculation. And I wanted to show in the talk some extra result, which I will not show. I mean, not show the proof, but I will show the result. So the second part is just some exercise for the participants. It has to do with primitive recursive functions. And even if you know primitive recursive functions, it might be not obvious to show this. So to assume what? A primitive recursive function p, and in p, primitive recursive. Then function f is primitive recursive. Where? What? F of x is 0. Is g of x 0. F of 0, 1 is g of 0, 1. And f of x plus 1, y plus 1 is h of x and 1. F of x of f of x of g of x 1 and f of x plus 1. Now this doesn't like, it's not the usual primitive recursion which you know. Now what's going on here? We have primitive recursion with parameter substitution. It's already non-trivial to show that primitive recursive functions are closed in a parameter substitution. Moreover, I have here a simple nested recursion. So the function f of
We classify the brackets.
some
F has two arguments.
f has two arguments, yes. So p is yeah. H has many arguments. It's important that this one is showing up with a different argument of h. So what do we have here? We have here a recursion where the main recursion is on x. So in defining f of x plus 1 and something, I can assume that I know what f of x is. Now plug here in the second argument again f of x. And then the second argument p of x1. And then I close all brackets. And then comes this one. Now I do subsidiary recursion on 1. So there are three things involved. And now the question is, why is this the case? And why is this not the Ackermann function? Well, the Ackermann function is, well, this is a sort of what is called unnested. So this shows not in a nesting with the other one. Unnested multiple recursion. And I now put parameter recursion, simple nested recursion, and unnested multiple recursion into one scheme. And the resulting function f will be primitive recursive. And when you just try to prove this using course values recursion, you will not succeed. It's somewhat difficult. And I have set up a nice proof using term writing systems. So I move this equation system to a nice rewrite system. Then I classify the derivation lengths, which are primitive recursive, and then by some general result, it comes out that the function defined is primitive recursive. So, but I want to stop here. Interested people can show the proof, but not today. So my time is basically over. Okay, so much for today. Questions? No? Nothing, yeah.
Yeah, it's actually always.
Oh. Okay.
Yeah, no, yeah, I think I'm good with mostly want to talk about the definitions. So yes, I think it's kind of look very similar to the say business of kind of verifications that you need to obtain this optimal balance for Haas.
Yes.
For Haas, not exactly this, but very similar.
It's very similar. So when you have no variables involved, then basically you have, so you can basically identify a term fk e1 en with eta omega k plus, well, it depends a bit on where you are. Omega, well, let's say omega to the n times k plus omega to the n minus 1. Then here you have 1 plus omega to the 0 times 1. Okay. And this is basically the order times of this. Roughly. Right.
So no, what you mean, okay, in X group it's very possible?
Yes. The lexicographic path ordering behaves like a Veblen function with n variables.
Okay, no, wait a second.
Yes.
Because I think if you want to get to Veblen style, then I'm concerned about this item 2.3
Yes.
and the last conjunct. So now it says that as
There's one which is deleted.
Right.
And you have here for all n, we have pk is smaller than.
okay.
Yeah, that disappeared from the.
Okay, no. That was indeed, yeah.
Yes. Otherwise, it's dangerous. It could be non-terminating. So this conditional subterms is necessary. Yes. But you're right. I was a bit too quick in wiping out, and but the proof which I gave is fully following the correct definition.
Okay.
But so what is?
But please then explain this to why precisely we see that. So on one hand, we have this here in your account we have quite small, or the types actually.
Yes. So there's this big round conjecture of Sichon, and basically the G hierarchy of this number. They correspond to the fast-going hierarchy like this. So, and that was the idea that he wants to relate the so-called slow-growing hierarchy with the fast-growing hierarchy.
Yes.
And now, the slow-growing hierarchy was also in gaps. You start with 0.
Okay. Right, it's more like solid.
Yeah. Now, you have to go high up to reach the Ackermann function in variables. Now, what is the point? The point here is where does this pointwise effect come in rewriting? And the explanation is as follows. So I have S rewrites to T. What does this mean? You have locally some left-hand side. And here on the right-hand side, you have term. Yeah? Then you have here some substitutions, minus stuff. And then the rest is context. And this is basically what the rewrite step is. Namely, in a term, you localize the occurrence of a left-hand side, and you replace it by a right-hand side under some substitution, giving these parts where the variables are in. And now, if the rewrite system is finite, you have the magical number Z, it's the maximum taken in the depth. On the right-hand side, such that there is a root in R. And this D is the important number because basically it means that clauses like here, they only apply in some sense to L and R. And they are locally under control by the number D. And the number D is the pointwiseness in the proof. And the rest is stability under context and monotonicity and whatsoever. And one has to exploit this. And basically, the number D says that if you apply these rules, this one here, or this one here, only in a way that it nests maximum many times. But that's the pointwiseness. This is not happening too often. And then this is reflected in the interpretation function, where, as you have seen here, I plug in this D. And D is an important point. And the D is the same as having the D plus 1 over here. And this means in these terms, I can use a D plus 1 fold iteration of those terms. That's somehow the magic. But now the question is, what type of general result can you make out of it? So can you so this is a concrete lexicographic path ordering. But can you make it more general into the sort of arbitrary determination only? And for some time I was believing if you have, let's say, an ordering which terminates on the basis that it fulfills the Kruskal conditions, I wanted to prove multiple recursive derivation links, but that was wrong. So the uniformity coming from the lexicographic path ordering is different from the uniformity you can extract from Kruskal arguments. So Kruskal argument is too broad. Now between Kruskal and lexicographic path ordering you have some sort of transition. But it's unknown where you have the jump from the slow to the fast growing hierarchy. And that's somewhat interesting, but it's open. And I'm somewhat interested in this open problem for more than 30 years without having a good idea. The only thing what I can tell you is how this proof works, more or less, where these numbers of iterations showing up and the numbers of iterations under control, that's all fine. And there's a corresponding result by Dieter Hofbauer, where he plugged in here a different comparison of subterms. Then he used the multiset of subterms of S is bigger than a multiset of subterms of T. And then the derivation lengths will be bound by primitive recursive function. So then this collapsing function will move into the binary Veblen function, which is not so surprising because the multiset operation is not a lexicographic comparison in this way, but it's just basically using omega powers, and then you can go along with simpler functions. Mm-hmm. Okay, that's it. We should stop the recording. So was there some external in?
No. Checking the email, but well.
Anyway, that's a lot. Yeah.